Section 2.4 covers the product and quotient rules of derivatives. So we found the derivatives of some mixed type functions. So when we looked at the basic rules of taking a derivative, we could take the sum of two different types of functions. And if we did that, we can take the derivative of the function by taking the derivative of the first term plus take the derivative of the second term. So that was fine, doing a sum of two functions, two different types of functions, because we could use the sum difference rule. However, it turns out if we want to take a derivative of a function like g of x equals 7x squared times natural log of x, it's more difficult. In fact, the derivative you would anticipate may be just take the derivative of the 7x squared and then times it by the derivative of natural log. That would not work out. So when you multiply two different types of functions together, the derivative is not the derivatives of the two individual functions being multiplied. So this is what the product rule does. It allows us to take a derivative of two functions being multiplied. Let f and g be differentiable functions on an interval I. Then f times g is a differentiable function on I, and moreover, f times g, the derivative of f times g is equal to f prime times g plus f times g prime. This rule is what we call the product rule. And it's obviously called the product rule because we're multiplying two functions together. It's the product of f and g. So how do I take the derivative of the product of f and g? So you take the derivative of the first function times the normal second function plus the normal first function times the derivative of the second function. You can show the product rule by going through a limit definition. I am not going to show where the product rule comes from. I will show some examples of the product rule and being able to take two functions individually. So let's look at example 1. Let's take the function g of x equals 7x squared times natural log of x, and we will find the derivative using the product rule. The product rule says we're going to split this into two parts, a first function and a second function. The first function I'm going to let be 7x squared. So I'm going to take the derivative of the 7x squared. That is 14x to the first. Then I'm going to multiply that times the normal second function. That second function is my natural log of x. And then I do the opposite. I take the normal first function, 7x squared, and I multiply it times the derivative of the second function. My second function is natural log of x, so derivative of that I should know is 1 over x. So the product rule gives you this, 14x to the first times natural log of x plus 7x squared times 1 over x. You can make that a little bit nicer. The way you would do that is you just write 14x natural log of x plus, notice this 7x squared. When I divide by x, one of the factors will cancel out. So you're just going to get 7x to the first. This leaves us with a derivative of g equal to 14x times natural log of x plus 7x. And this is how the product rule works. We look at two pieces being multiplied together. We say take the derivative of the first piece times normal second piece plus normal first piece times derivative of the second piece. And that's the product rule. I had said we're not going to show a proof of the product rule, but what I will do is show how the product rule does give you the same answer as what you would have gotten with basic rules along with doing some clever algebra. So again, I'm not going to show a general proof of the product rule, but I will show that the product rule works on an example that we could do both with our basic rules and with the product rule. Let's take a derivative of this f of x. This f of x is equal to 5x to the fourth plus 2 quantity times 6x to the 8th. We're going to do this two different ways. The first way I'm going to do this is by utilizing the product rule. So the product rule tells us that if I want to take the derivative of this function, since this function is two functions multiplied together, or two expressions multiplied together, I can take the derivative of the first expression times the normal second expression plus the normal first expression times the derivative of the second expression. Let's see how that works. So the derivative of the first expression would be 20x to the third plus 0. I'll just write that as 20x to the third times the normal second expression, that's 6x to the 8th, plus the normal first expression, that's 5x to the fourth plus 2, times the derivative of the second expression, 48x to the 7th, and that would be how you would find the derivative using the product rule. I'm going to come back to this in just a moment, so I'm going to leave it up there. Now, this one you could have actually have done using not just the product rule, but algebraic rules of multiplications of polynomials. So let me give you what I mean by that. Let's rewrite f of x into a single polynomial. If I do that, I just need to distribute 6x to the 8th into the polynomial on the left. If I do that, I will get 6 times 5 is 30. X to the 4th times x to the 8th is x to the 12th. Plus 2 times 6x to the 8th is 12x to the 8th. Now let's take a derivative of that function. Remember, this is just a rewrite. This is just a rewrite of f of x. So now I take a derivative of that. 30 times 12 is 360 x to the 11th plus 12 times 8 is 96 x to the 7th. So if I utilized algebra and then my basic differentiation rules, I would have gotten 360 x to the 11th plus 96 times x to the 7th. Now, is that the same thing we got up here? Well, since we've already taken the derivative, let's go back and multiply and do some algebraic properties. 20 times 6 gives you 120 x to the 11th. That's what you get when you multiply the first piece there. The second piece, you're going to have to use the distributive rule. 48 times 5 is 240 x to the 11th plus 2 times 48 becomes 96 x to the 7th. And you can see when you combine like terms, you end up with 360 x to the 11th plus 96 x to the 7th. So notice that either using our basic differentiation rule along with some algebraic multiplication or using our product rule gave me the same answer in this case. Now, this is just this case, so it doesn't prove that the product rule always works. But again, if you look in your book, you can see a general proof that the product rule always works. So the product rule always works. And you can also see that just taking the derivative of this piece times the derivative of this piece would not work. I want you to try to find the derivatives of these two functions using the product rule. Go ahead and push pause on the video and do that.